Check, check. Okay, let's get started. So, I have nothing against popcorn. I'm a very big fan of popcorn. When I went to take my qualifying exams in grad school, I took, bought a bag of popcorn and brought it in and ate. I only realized later that I annoyed the hell out of everyone else from my crunching. So, I think this won't be an issue, but I thought it was kind of funny. And as far as I know, the people I bothered still passed, so that's good. Next Monday, my office hours from 2:30 to 3:30 I already said are canceled. I'm also canceling 12 to 1 because there's a deep learning for robotics talk from noon to 1 in Beckman. that I think would be good. I would enjoy it, and I think you guys would enjoy it as well. I am adding office hours from 9:30 to 10:30. Okay. Questions on that? All right, so today we are talking about using neural networks to generate things. Okay? The first thing we're going to be talking about is what's called neural style transfer. So this was done, I believe it was 2015, this paper. It basically said, wouldn't it be cool if we could take any old image and apply to it some style from another image and come up with kind of the combination of the two, but in an important way. It's the content of the first image and the style of the second image. So it's a photo of my house in a Van Gogh style, you know, or a picture of you in a Cubist style, you know, Picasso style, something like that. And it's unclear really how you use a neural network to do that. I mean, what do we even feed in? We feed in these two? But then what do we use as our labeled data? Do I have to go, you know, by hand, go into Photoshop and create a bunch of stylized things? No. So this is what we're going to look at, and this is neural style transfer. Does the problem make sense? So we have an image, and this is our content image, let's say, and we want to add to it a style image, and I don't know what the style is. Let's say it's some angry type of style, right? And we get out. I don't know what this would look like. Maybe. I'm not sure what exactly would be right. But this is what we're going to call the combo. Okay, the style from the content from the first and the style from the second. Okay? Let me just show you a couple of other pictures just of things we might be able to do with this. Let's see, I think there's some, whoops. So for instance, here's one, content first, style second, and we've got that. Or here are some others. So the cat that turns into a very scary looking cat. So we're going to use a neural network to do this, but we're not going to be training it in the standard way. Just in the same way when we were looking at visualizing convolutional neural networks, we did some work in terms of doing some learning, but not on the weights. So we are going to actually learn this image in the sense that we're going to generate it using gradients. So we're going to have to define some loss function and some way basically of this getting a noise image, just random, turning into this. Okay? Epoch after epoch after epoch. Training. And we'll just be computing partial derivatives of each pixel. Just in the same way that we were doing adversarial images by taking an initial image and then tweaking it. Here we're going to be taking random noise to begin with, just like we have random weights when we're training weights. And we'll just make it closer and closer to something that minimizes loss. And that's going to be really the key. How are we going to choose a loss function that will come up with this, given these two?
So it looks like, maybe this is very early on, but it looks like we have sort of like more realistic images on the left, and then we have these sort of artistic styles, like is it like the style, like from this, could you theoretically do the same thing, like having something that looks like very artistic, having like a real image, and then making like the artistic thing look more real? Could that be like a style of the work?
Well, we could try that. Well, you'll learn kind of what we mean by style in a bit, and what we mean by content. And so it'd be very interesting just to flop those around the other way and see. Other questions? Okay, so we're going to start with a trained neural network. What should we use? VGG sounds good to me. VGG 16, 19, we'll pick one of those. Let's say 19. Okay, so start with a trained train, right? That's really important that it's trained, because without it, it's just random weights. That doesn't do us any good. And so this trained VGG19 already knows lots of both low-level and high-level patterns, right? These features. And that's what we're going to take advantage of. So we're going to define a loss. The loss function is going to be defined basically as the loss, two losses. One, the style loss, where we'll just compare the combination with the style image, plus a content loss, comparing the combo to the content image. Right? And I suppose maybe I'll put some I's here for image content, image style, and image combo. So this is the style loss, and this is the style image, the combo image, and the content image. Does that make sense? I mean, it's like, okay, we've just pushed the problem back slightly farther. Both of those still seem hard. Anything we would want to do this, though, any changes we might want to make to this so far, assuming we could define an appropriate style loss and an appropriate content loss. I like weighting. So, right, because maybe the content loss is 5 times, right? We look and we say, wow, it really stylistically good, but we lost all the content. So we want to have some sort of weighting. Let's put in, I don't know, a beta and a 1 minus beta. Right? We really could do with just 1, but it's common to put in these. So that sounds good. Other than that, any changes we want to make? All right. So let's now try and look in specific at one of these. I'm going to look at the content loss first because it's a little easier. How does this sound? I'm going to go back to the other image because I like it better. Oh. Well, I don't know how that got big, but I like that. Or do I? No, I actually don't. So let's go back to here. So this is an important one. It's a cell. All right, anyway, there we go. So how about we just look at the pixel difference between this one and this one? Good, bad, indifferent? Any thoughts? Let's look at this part here. This looks like the house that has been swirled. Doesn't it kind of? It looks kind of like this swirl has happened to it, right? To this house. So if it's swirled, individual pixel and the corresponding pixel over here, are they going to match? Not at all, because it's been swirled. So direct pixel correspondences between here aren't going to work. Instead, we want something more abstract, some higher level abstraction. And if we look at our neural network, and the layers in our neural network, so we've got coming in some image, and so this is our neural network, and it basically gets transformed, right? It gets transformed. We have the output of the first layer, which looks like some set of activations, right? Some height times width times the number of features. And then that gets transformed. Sometimes it's the same size. Often that turns into, let's say, a smaller height and width, right, when we reduce the size. And often when we do that, we increase the number of features. Does that describe, all right, how our neural networks work, basically? Convolutional neural networks? What could we say about the features, let's say here, in the very first layer?
Pretty high level.
Tell me about that. How much are we looking at? What's our receptive field for any one of these? Right here. How many pixels were we looking at in our original?
3.
Three.
Pretty low level.
3 by 3, right?
Yeah.
9, so,
Yeah.
but that's not very many. Yeah, it's got to be low-level features because we can't even see. We're looking through this tiny little peephole, the postage stamp, and so we can only be detecting low-level features. And in fact, you remember on Mondays we saw, as we were looking at the cat and kind of what happened there, that there was, well, if we had looked at the activations map themselves, we would have seen, let's say, kind of horizontal line detectors. Some of them would have, some of these features would have responded very well to horizontal lines, some to vertical lines, some to particular colors and so on. So these are low-level features. What about the next level? Lower or higher level? Higher. One reason is it actually has a larger receptive field, right? So it can see more pixels in the original image. And a second reason is it can build things off of these low-level features. Okay. Maybe one of these features is a horizontal line feature, and another feature is red. Well, this guy could be doing red horizontal lines, right? By composing these two features. So higher level features. And as we go, this becomes higher level. Right? As we go to the right and down the something. When we get to this level, these are fairly abstract. Very high level. They might represent things like, because remember, to the right of this, we have maybe one fully connected layer or two fully connected layers, and then we have our outputs, right? So all the things that we need to recognize have to be coming from not too much manipulation beyond these features. So we might have things that either directly or pretty closely directly relate to, let's say, a house or a river or a tree or sky, stuff like that. Does that make sense? So we might have, let's say, one of these features, let's say this one. If we pull this out, might say, for instance, I don't know, let's say this, if we could figure it out, was houseness, okay? It's pretty closely related to being a house. So maybe we would have like that, right? High things here, low things there. Kind of representing there's sort of a house, or maybe multiple houses, we don't know, but there's house stuff going on in the bottom right of this picture. So that's kind of content-ish, right? That's fairly content related, as opposed to if we're looking way over here where we're not doing much with content at all, right? We're doing little 9x9 snapshots. So my claim is the last layer, the last convolutional layer, is a good place to be looking at content. Okay? It's not as directly located in the picture as earlier, right? Later on, your receptive field becomes very big, right? The receptive field of each of these pixels may be the entire image, or maybe much of the image. But nonetheless, we get an idea that, let's say there's houseness going on here, assuming down here is what I said, maybe it's across here. So let's just see if there's houseness going on here, and houseness going on here, which in fact there is, right? So let's compare, for this feature, the content image and the combo image. And I guess it's not really the case. So this is fix this a little bit. We are going to come over here. So we have our neural network. We feed in I sub content. We feed in I sub combo, which remember to begin with is going to be random noise. These will go in to the neural network. Hey, maybe we'll even use a batch, so we can run them all at once, or both of them at once. And we'll come up with our final layer, final convolutional layer. We'll have, I guess we'll just run them through separately. So this will be A at K sub content. And this will be A at K sub combo. Right? Just the final activations. And they both look like this. Yes?
So I was wondering, when you said that it's still houseness in the combination image, do we know for a fact that if, like to our eyes, it might look like it still has houseness, but since the neuron has only seen like a very narrow range of what a house is, then it won't be able to pick up the houseness of the image?
That'd be a problem.
And
Yes.
I'm just asking, like, if in practice, if that's
Yeah,
true, if
that's-
like, pick up.
Yeah, I mean, that could be an issue. It does work for these sorts of things. VGD19 happens to. So maybe some of the images that are fed in, the millions of images, happen to include, what would we call this, non-realistic
Yeah.
paintings of things. So, okay. And maybe it doesn't actually have a concept exactly of houseness. Maybe it's
Right.
some lower level things that are then being combined later. You know, maybe it's, I don't really know. Maybe it's windows. Maybe it's, you know, long. I don't know. Does this make sense so far? And now let's just compare these. So basically, let's subtract these and look at the mean squared error. Okay, so we're going to say the loss of content, let's just say x and y, or x1 and x2 equals the mean squared error of the activation I want to write that. All right. So this is K is the last layer. I'm going to say here. And 1 and 2 just represent our different input images, 1 and input image 2. Okay. So again, we feed in the content. We look at the activations of the last layer. We feed in the combo. We look at the activations of the last layer. And we just do a pointwise subtraction and then sum squares.
Wait, so to clarify, are these going into two separate?
Same neural network, same exact pre-trained, because this is the neural network.
Yeah.
That's it.
Okay. And then the back propagation there was only happening from the I combo.
It's only, we're only going to be changing the I combo. The content and the style we leave alone. We're going to change the I combo. So to begin with the random noise, this loss is going to be quite high.
Yeah.
Right.
Oh, so you are adding random noise to the combo to make, or to the original to make the combo, or?
So here's what we're going to do. Let me show you the whole training loop, and then maybe this will make sense. Let's do it here. I like that. I like this. Well, we'll get rid of this one. So we're going to basically say I combo equals random. for some number of epochs. It's actually like one line. What are we going to do? What are we going to change? Are we changing weights? Not the weights of the neural network. What are we changing? I combo. Yeah. So I combo minus equals, right, because we're trying to reduce the loss. Let's say some learning rate times, this should look very familiar, times what?
DL, DI combo.
Partial L, partial I combo. This tells us how much increasing the particular pixel value in I combo increases the loss, so we will decrease. And we'll use a little learning rate. And we'll probably throw in an optimizer, but I'm ignoring that for right now. So that's what we're going to be doing. And notice we're starting with just random noise. We could start with one or two of the original images and kind of have it pull one way or another, but it also works for random noise. So does that make sense for the content, how the content is going to be closer? We haven't yet looked at how we're defining the style. So let's look at the style. The style, when we're looking at artistic style, do we care about low-level features? I'd say yeah. I mean, like a little brush stroke or something might be a little feature that is representative of our style image that we want to capture. Do we care about higher level features? Well, what about, for instance, the swirl? That's a lot bigger than 9 pixels, right? You can only get a swirl by having some feature whose receptive field is at least as big as a swirl. So that's farther down in the neural network, in the layers.
Is there some formal definition of style? Because configuring the style is like separate from that swirl in the sky. It's mostly just like,
Well,
and that swirl is actually content.
there are a lot of swirls, right? There's a swirl here and a swirl here, and to me, they look like they're part of that they're seen over and over, they're seen more than once, and that it seems like it's part of it, right? The color choices, the color palette is kind of it too, right? So there can be style at the low level, and there can be also style up at the higher levels. So what we're going to say is, we're going to go ahead and just grab some representative layers. We'll grab like 5 layers. We'll grab the first layer, and maybe this layer, and this layer, and this layer. We're not going to grab the last layer, because we know that's really abstract. So we'll take some layers along the way. And now our problem is just, how do we determine loss layer to layer? And we'll sum them up. Okay? So for the style, loss of style equals the summation of loss style at a particular layer. And we'll define which layers we want. We'll just pick them out. Okay, so our problem is like infinitesimally easier now because we just have to deal with one layer.
So if you flip these two, the style and the target, it wouldn't work very well, right? Is there a way if they're defining a style one, because you couldn't really sharpen the Van Gogh and make it work?
It would be interesting to see what happened. You would probably have a thing up here, whatever that is, and a steeple and some other stuff. And yeah, I mean, that'd be a really interesting thing to see what happened. And we have this notebook, and we could just swap the images and see. So someone do that and tell us on Monday. But it probably wouldn't be quite as effective because this isn't, there's not as clear a style here. But there's something about this that would probably be reflected. But yeah, there are reasons we choose those very stylistic images as style images. So now how do we do the loss of particularity? Here's what we're going to do, and this is a tad complicated, but let's look. So we're going to have our activations at a layer, right? Height, width, features. So this is our activation. We're going to take a single feature, right? So we're taking this, and we get height, width, right? This is just one. This is feature I. And now we can pull out, let's say, feature J as well. These are supposed to be the same size. Okay. Remember I talked about like a red horizontal line? I said maybe in the first layer we have one feature that's horizontal and one feature that's red. If this was red and this was horizontal, any places where they were both high would be places where in the original image it's a red horizontal line. Okay? So we might want to know what is the correlation between these two features? How much do they co-occur? So we're going to take these two, and I'm going to do a dot product. Okay, so we're going to basically just take this times this, plus this times this, plus this times this, plus this times this, all the way up. If you want, just think of it as we unroll it. Right? We flatten this out to one dimension, flatten this out to a one-dimension vector, take the dot product. And that tells us how correlated are these two. Right? If they're perfectly correlated, wherever there's a red, there's a horizontal line and vice versa. If there were never any red horizontal lines, the dot product would be 0, right? And we're going to do this. So I'm going to actually write this as, let's say, flatten this into h times w by 1. And this one, flatten h times w by 1. And then here, we're going to do dot product. The result of dot product is write a single number. And we're going to build a matrix. So 1 through f with the number of features, 1 through f with the number of features. And we're going to compute this dot product for every combination of features I and j at this layer. And again, this is a single image that's causing this activation. So for this single image, we're saying, how do these features correlate with one another? Along the diagonal axis, what will happen? Will these numbers be big or small? They're going to be big. They're completely correlated, right? Every time feature I occurs, feature I occurs. So these are big. And in some places, they're going to be some big numbers. In some places, they're going to be small numbers, right? So this one might be, this is j against I, and that might be big. So this might be saying red horizontal lines, yeah, happen a lot. This is called a Graham matrix. These correlations, and it's symmetric, right? So correlation between I and j is the same as the correlation between j and I. So we're going to compute the Graham matrix for our two images. Really, we're computing the Graham matrix for the activations in a particular layer for our two images. So we compute let's just call it gram sub content at layer 1 and gram sub style at layer 1. Right? And when I say gram sub content, how do we get gram sub content? We take the content image. Let's not do the content and the style. What should we do instead of the content? Combo, yeah. That's the one we're interested in, right? The one on the right, comparing that to the style. So we feed the image in. We get the first activation layer. We compute the gram matrix. We do the same thing for the style. We subtract them, and we take the mean squared error. So this tells us, for the very finest level details, how does the combination match the style? If this one has red horizontal lines, then the loss will be less if this one has red horizontal lines. Do we care where the red horizontal lines are occurring, though? This doesn't measure where it occurs at all, because we just flattened it out and did our dot product, and we completely lost our spatial information. In order for us to get a large dot product, we did have to have a red feature co-located with a horizontal line feature. Okay? But once we've computed that dot product, we don't know where it was. We just knew there were some red horizontal lines. If the combination has red horizontal lines, our loss will be lower. So that will tend to make this combo image have the same low-level features as over here. Okay? The color palette may be low-level features, for example. Does that make sense? We do that for the first layer, and we do it for like 3 or 4 other layers down the line. We sum them all up. That's our style loss. We already saw our content loss. We set an appropriate beta such that they combine nicely so we don't totally lose the content, but also don't lose the style.
Would we want to weight the different style like?
That'd be something you could do too. Yeah, you could certainly say instead of uniformly weighting the 4 or 5 different style layers, you might find that it's better if you do some weighting of those. And you're going to have to do that by eye, right? You're going to have to look, and it's possible for some style images, weightings, different weightings would be better or worse. And I'm impressed that popcorn, like I couldn't even hear it. I saw it, and I could hear nothing. So, all right. Any questions on this? How fast is this? It's slow. Because we got to go through the learning process, right? We got to go through. We need to do however many. I guess we'll call them epochs. Each epoch is really going to just be one update of the image, right? But we have 1,000 maybe we might need or more. So what if you wanted to create a neural net that applied Van Gogh styling to any image? Yeah.
Where you had the eye combo, you just fed in noise, you would make that a neural net, right? And then plug it in there. You do that.
Well, is there any way we can avoid the long loop training? Yeah.
You can predefine a gram style, maybe.
You could predefine a gram style, but if you predefine the gram style, you still need to be going through and taking this random value, right, random image, and updating and updating and updating and updating. If only we had some way of taking, like, this image, feeding it through a neural network and getting out this image. What do you need in order to train a neural network to go from an arbitrary image to an arbitrary stylized image? You need training data. Do we have training data? How do we have training data?
Because we just made some.
We made one. We have now one instance of training data, right? This is our input and this is our desired output. Can we make more? We can make as many as we want, right? We could fire up 1,000 machines, run them all in parallel, get 1 million different training examples, train ourselves a brand new neural network. So, but it only works for one kind of style. This is the approach we'll use for any sort of style. Questions?
So like for that neural network, you want to use very different images for the training probably so that it could not just learn how to deal with like houses or something?
Yeah, you don't want to just deal with, you'd want to, maybe you take the ImageNet data, or, yeah, you'd want it to be something similar to what you would see in the wild, so depending on how you're deploying this.
How are you defining what's a correct answer for this?
It looks good.
But that's, okay, like I just don't, I don't think I understand how you're like validating this model, other than just saying, oh, it looks good. Like what is the end goal?
I hate to say more than this. Things that we as humans kind of say, yeah, it kind of looks like the content, it kind of looks like a style, that's cool. That's it. So that's how we would define our weights.
Isn't that, I mean, the same way we validate any kind of convolution thing, and people look at it and say, oh, like, okay, that looks like a dog. I guess that's right.
There's some difference in that we have labeled data normally, right? And I guess we have to label it, and so we say it looks like a dog. Here, is this that plus that? I say yes.
So would you, while you're doing this process, would you have it like print the image and then you just like, look at it for each epoch or something, or would you like print it every 100 or something?
Yeah, you would. In fact, that's what this notebook does. It prints every so often. So yeah, because how long do you need it to run? I mean, what's good loss? You can only tell by looking.
When we're picking our features, is it sort of randomly picking out different like features or layers and then sort of like choosing what we think is the best ones, or is that like I'm looking to sort of like the features that we're picking out for the style?
For the VGD19, we would just say like, let's do 4, kind of sort of evenly spaced from the lowest level to before the highest level.
Yeah, kind of a similar question. Does it depend on...
But what's interesting is it does tend to work for multiple kinds of styles. So this is not fine-tuned for this particular style content combination, or even just this particular style. Once it's, I was going to say once it's trained, but you're not really trained. This algorithm, once you've chosen the weights and chosen the layers, seems to work pretty well for a variety of different styles.
That was quick.
Would GAN be useful for doing this type of
GAN. Let me just write that down a second. Yeah, the perfect segue. So, generative, adversarial, network. That's our next topic. Okay, GAN. So what a GAN, we don't have as good a picture or a demonstration here as we did for the neural style transfer. Because the neural style transfer, this describes it. This is what it does. The GAN is somewhat different. So let me kind of provide a background. We're trying to come up with a neural network that will generate fake things. Okay? Fake like what? Fake Amazon reviews. Why would that be useful?
If you have a product on Amazon, you can make it seem like it's really good.
Yeah, a product, or I, as your competitor, can make it seem really bad. Yeah. Okay. What else might we want to fake?
Faces, deep fake?
Faces, deep fake, faces on top of bodies, closed in various ways, yes. So we could fake, what are examples of fakes in the past? Totally in real life, not digital at all, yeah.
Fake emails? Or like
Fake emails, but those are digital, it turns out. But yes, fake email is a good example. What about in real life?
Fake IDs.
Fake IDs? Actually, that's okay. Let's do the fake ID. All right, you're the fake ID generator. All right, so we've got a generator. It's a neural network. All right, and it's producing fakes. It has an input. This input is often noise. We'll come back to that in a little bit. So it's going to produce fake. So you put in some noise and it gives you a fake ID. Okay? And then we've got the bouncer. The bouncer, with a fancier name, a discriminator. Okay? The bouncer can either get in a fake or it can get in a real thing, whatever this thing is, right? ID. And its job is to tell whether it's a fake or not. So it's spitting out what? Say it again?
Like a binary,
Binary, yeah, 0 or 1. Actually, it's in the range 0 to 1, right? Now, as far as the generator is concerned, the discriminator is its adversary. And sort of vice versa. As far as the discriminator is concerned, the generator is its adversary because it's trying to fool it. So you take your ID. You take your ID in, and what's the guy's name from Superbad? McLovin. Yeah. Something like that. And it just says McLovin, right? And that's it. That's it. It just says McLovin, right? And you take it to the bouncer and assume this was way back when, okay? And the bouncer looks at it and kind of says, okay. Or maybe the bouncer says, this is not very good. Every time I've seen an ID, it actually has a picture on it. And so, no, it goes back and it says, oh my goodness, I need to learn to do better. I'm going to now put a picture of a cat. And dig in, and it says this, I've always seen IDs that have humans as pictures. This is a fake, okay? So there is this evolution, a competitive evolution that's causing the discriminator to get better and causing the neural network generator to get better. Each one is pushing the other to get better. It's like spam. It used to be in spam emails. They would send out, grow your penis by, taking this special supplement, just click this link, right? And then the spam detector started saying, oh, if there's the word Viagra or penis in it, that's spam. And then the spam guys got a lot more sophisticated, right? And they started sending out the spellings like this, right? And the spam detectors, on the other hand, right, increase their guard. And it goes back and forth, such that they're both much better than they used to be. That's what we're going to do here, such that we cause this generator to become really good. We actually don't care about the discriminator. The only reason we want the discriminator to be good is to have a good opponent for the generator to force it to be good. Does that concept make sense? I'm not a racist, just it might be confusing as people come in. All right. Let me show some examples of things you could generate. So these are some examples of fake celebrities. All right? So there's basically a discriminator. Discriminator gets, right, some real celebrities. It's got to have some training to know what are good values. And then we try and see if we can fake it here. And so, yeah, these are some examples. And these are also, over time, right? They used to be pretty small, and like, I guess he's a character actor. But they get bigger and better, and totally unreal. Or MNIST, right? You remember MNIST? This was a generator that learned to generate reasonable looking digits. Because we basically had a discriminator where we were feeding in real MNIST digits as opposed to the ones the generator was creating. And so it could come up with things like these. Or, let's see, is it here? Anime creator. So this one is slightly different in that we don't actually feed in noise. We feed in things like red hair. I'm not sure. I think it just had a list of kind of features coming in. So there was some noise, and then there was a vector. One part was for the hair, which color it is, and some other sorts of features about it, kind of the desired thing you had. Maybe, I don't remember what it was besides that, but I know at least hair color was one of them, and there were some others. So it provided a way to generate realistic looking animes that had some characteristics you wanted. So there, it was not just noise. This was noise plus, let's just say at a minimum, hair color, but it was actually other things as well. Okay. All right, so how does this work? Well, really, it's fairly straightforward. So we're going to, for some number of epochs, we're going to train the discriminator, okay, on real call them items and fake items. All right, so this would be G of Z for random Z, right, drawn from some distribution. What are the labels going to be for the real items? Right, this is a supervised learning problem. We know exactly how to do this. Right? We're feeding in an image, let's say, and what's the label? 1. And for these guys? 0. And we'll pair them 50-50. Right? So we just generate a bunch of fakes, have a bunch of reals, feed them in the network, train a little bit. All right? To begin with, this discriminator is going to have such an easy job, right? Because the real items have a lot of structure, and the fake items are like random noise going to a random neural network. Okay? So it's just random crap coming out. And the discriminator will just figure out kind of the minimum it needs to. Then we need to train G. And I'm going to just say, so train D for a while on these. And then we're going to train G. Actually, we don't even know how to train D yet, do we? Do we have a loss function? We have the inputs. There's 3 things. I don't know if I've explicitly said this. So for a neural network, or for deep learning, you need 3 things. You need, what's one thing you need? Data. What's another thing you need? Say it again? A loss function. A third thing you need is an architecture. And maybe hyperparameters too, but we're going to have to be doing some hyperparameters. But these are the 3 things you need. Do we have data for this problem, for the discriminator? Yes, we have 1 labels and 0 labels. Do we have a loss function? Not yet. We didn't actually say, what's it going to be for loss? So loss of D equals binary cross entropy. Exactly. We actually know how that works. What about the architecture? Do we know what's coming out at the final stage of the neural network? It's a single value, and the activation function is sigmoid. Right. What's our input? Whatever these things look like. I mean, if they're pictures, if they're sounds, whatever, that's what it's going to be. And we'll have to set up the architecture appropriately. If it's images, we'll probably use a convolutional neural network. We're just going to have to figure that out. Okay. You with me so far? So we have everything we need to do this training. Now we need to train G. So what the heck do we want the loss to be? Yeah.
Good question. Is that realized and fake items?
Yeah, that's an ampersand. Yeah. So when do we win? What's a low loss and what's a high loss? What are we trying to do?
We get a high loss when the screen picks 0, and then
Yeah, we get a high loss when we can't buy our beer, right? He says this is a bad ID. We get a low loss if he says, oh yeah, this is indeed a real ID, right? So we want a low loss if D of G of Z equals 1. So we're going to pick a random value. We're going to feed it through our generator. We're going to take that output and feed it into our discriminator. And if we can get the discriminator to say 1, we win. And we want a high loss if this equals 0. And in fact, since it's continuous, we'll have a continuous loss. So what will work for this? We know we want a loss based on a number between 0 and 1. And we'd like to have sort of an infinite spread out of it, right? So that if it's a 1, we get 0. And if it's a 0, we get basically infinity. Do we have any candidates? Can we make something up? Danny?
Like inverse sigmoid?
The inverse sigmoid seems like a good candidate.
Oh, but negative infinity.
Well, if it's negative, you could always,
Yeah.
oh yeah, that's from negative to, yeah, so that's not quite. What about log of d of g of z? What is that going to give us? What's log of 0.5? Base 2. Log base 2 of 0.5. Negative 1. 1/4. Negative 2, 1/8. Negative 3, epsilon, for very small epsilon. A really big negative number, right? And what about 1? Log base 2 of 1 is 0. So this, if we throw a minus in front of it, that gives us a number in the range 0 to infinity. Does that make sense? And that's kind of how we design our loss functions. Like, well, where do we want it to be and what are we coming in? Let's make something up. Of course, a big bonus if it's differentiable, which this is, so that we can push our gradient back. So this is what we'll use for our loss function for G. We are going to pick a random Z. Calculate the loss of d of g of z. Backpropagate. The loss is using this as a value, right? This 0 or 1. We're computing the loss on this. So when we're back propagating, this is a function where we have to, back propagate from the loss down to D. So we're back propagating through D all the way up. It's just this very complicated function all the way up into here. As we're going back with our back propagation, do we want to update the weights in here? For sure, we want to get G to be better. Do we want to update the weights in here? We don't want to update the weights in here, because if we updated the weights in here, that would basically say, make the discriminator worse, right? Make the discriminator less able to discriminate me. And so, we back propagate and update the parameters of G, not D. D is locked while we're doing this. Does that make sense why? Okay.
Could
Josh.
we reward the discriminator while we're also training the generator to reward it with a positive one to encourage it to keep doing better at the same time?
We could. We did a bunch of things in here already. This is just one more fake item, really. And so it's one more data point that we don't really need to update along the way. It's a different loss function, so the gradients are going to be different anyway, so it's not going to really help us computationally. As we're moving backward, there's nothing useful we can get from that. Good question. Other questions? Yeah, go ahead. Santa.
So when they output these images, that's purely done by neural net. There's no kind of assistance in drawing, right?
There's no assistance in drawing. This is a pure neural net. As were those images you saw before of people, right? There's no help at all.
And it's convolutional?
As images, they would be convolutional. They are, yeah.
Okay, so whereas before convolutional net was reducing dimensions, this one's increasing dimensions?
Yeah, it would be. It'd be basically
Okay.
the converse.
Do you
Yes.
know how to do that? How to increase dimensions for convolutions?
Well, let's think about that. Do we? We haven't talked about it. So one simple thing you could do, just off the top of my head, would be just duplicating, right, columns and rows. But there's more you can do. I think it's a deconvolution operator would take you back to some higher. So there, in fact, one use of neural networks is to sharpen images or to scale them to be bigger without it being chunky and blocky. Right? And that's somewhat similar. Yeah.
So the generator and the discriminator would both be convolutional analysis?
If you're dealing with images, yes, they would be. Basically, so this would be convolutional where you're going standardly as we've done from an image down to a single value. And this would be almost in reverse. We would just have to figure out what our max pool operation was that would make it bigger instead of smaller. All right, let me give you an example. It's just something I thought of and have not proven out. But this could be one way you could use a game. Oh, let me just point out one. So I said they're hard to train, and they are hard to train. One failure mode is what's called mode collapse. All right. This is, okay, so imagine we're now to paintings. Okay, I'm a forger, and I'm painting paintings, right? And I just paint all these paintings, and I send it to the art dealer, and the art dealer, either catches it's a fake or doesn't catch a fake. And finally, I get really good. Oh, and what I do is I roll some dice to decide what to draw, right? That's kind of like the Z coming in here. Well, it turns out over time, I get really, really good at drawing the Mona Lisa. And so every time, whatever I flip, I say, I got a heads and a tails and a tails and a tails. I know, I'm going to do the Mona Lisa. And then you say tails, 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 100 tails in a row. I think a Mona Lisa would be good today, right? So you collapse down to, I'm going to just do single good output. So it gets really good at this particular output, but it collapses down to 1. Not very useful for it, because you know what? The art dealer, like, basically, how can they detect me? Yeah, like the Mona Lisas, I think Mona Lisas are fake, right? Fine, the one Mona Lisa that's real, I'll get that wrong, but every other one I get right, okay? And so they caught me. So then what happens in the mode collapse is actually what happens is I start finding that the discriminator does not like Mona Lisas. And so I shift away and I start doing the Andy Warhol Campbell soup thing, right? But unfortunately, like all of my Mona Lisas work over there, and it's like, I'm gonna now just do that thing instead to try and fill it in. So it's this, you're moving around where the discriminator keeps pushing you to go somewhere else. But still, we're in this single mode collapse where all still do is just output one thing. That's one failure mode for GANs. The other one quickly is this. Imagine, who here listens to podcasts? A couple people. So you know how a lot of times, or talk shows too, right? Someone calls in on the phone and it's a crappy, right? The host sounds really good and the guest sounds really crappy. Wouldn't it be nice if you could automatically improve the quality of the guest? So the theory would be something like this. Have a GAN with the generator taking in the low quality, I'll just call it low Q, and outputting high quality. And the discriminator has guessed high quality samples. Right, so you tell the guest to read the phone book for an hour into a microphone or something, and you get it nice high quality and send it to you, or you just have some existing high quality stuff. What could go wrong here?
It's going to end up, regardless of what's going in, it's just going to produce what the good guess samples were. I think it's not going to augment the lower one. Or it's gonna
Well, it is going to learn to have something come out that sounds like good, high quality guest, right?
I'm guessing
But
high quality does sound quite monotonic. Like they're gonna have the same kind of guests, things like that.
no, but this is for, let's say we train this for a single guest, right? This is the single guest. John Grisham or something. Let's say that Terry Gross was interviewing. Yeah.
Your GAN has no incentive to like actually have the outputting words be even recognizable words. Which is, like, the
It
same
does
as-
have it does have incentive to provide them to be recognizable words. Because if these are unrecognizable words and these are all of these are recognizable words, then a good discriminator could say, hey, this is gibberish and this is not gibberish. But you were onto something, yes?
Like in what order though? Like they could have the words be in a random weird order that would make sense to everyone's actually listening to.
That's a possibility, although you can imagine a really good discriminator would try and make sure the word order makes sense.
If
Santi?
it's one sound sample and then output it over again.
If it got into this mode collapse, it could learn one sound sample, but let's say it doesn't.
The words wouldn't match, it would be words that were from the samples, or it would be something.
Yeah, the low quality coming in was 7 years ago, our forefathers, and coming out is "Oh Say Can You See" by the Dawn's Early Light. But it's really high quality, and the discriminator can't tell the difference. So we would need to throw one more thing in there to make sure that the text that they're saying is actually the same. Is that an easy or hard thing to do? Well, if you upload a YouTube video, right, I'll upload my lecture, and it like automatically gets captioned, right? They don't have little workers in China sitting there doing that, right? It's automated. So we could feed this into a text. What is it? Speech, what do we call that? Text recognition? Speech recognition. And this to speech recognition. And that's pretty easy to ensure they're the same, right? Or very, very close. So we could put our loss function be both. It has to fool the discriminator, and it has to be the same. You're saying the same things. Yeah?
Isn't this super similar to what we talked about earlier as far as like the content is what the actual speech is and the style is the quality?
It's an interesting point. So the question, yeah, I wonder whether you could. Yeah, that's an interesting point. There certainly do seem to be similarities. Dan.
This would still allow for the high quality output to like just have a different sounding voice than the low quality input, right?
It would be what?
Like this would still allow for the voice that the like first network is outputting to just like sound totally different.
Yeah, it could sound totally different.
Okay. Yeah.
It could sound totally different, but it would sound like this.
Right.
Which is good, because the phone voice, you know how it always sounds so different than the high quality mic voice? So that would work well. Yeah. I suppose what you could also do is interview me and have high quality guest samples for John Grisham. And then I could go ahead and stand in for John Grisham. Right? That would work too. It's kind of more fun, actually. All right. I have some things to give you all. Let's see. First thing I want to give you. I would like you to take about 5 minutes and together with the person next to you, write up what you think would be a good exam question, including an answer. And if it's multiple choice, give all the choices.
So we receive one card.
One card will be sufficient. Yeah, you're going to one card between two of you. And is there any? Can you guys work with Rory?
Oh, yeah.
Did I mention for this class? Yeah, just a general example.
Oh, no, sorry. I didn't. Yes.
What, like, area? Oh, yeah.
The question you're doing could be from anywhere in the class, but the midterm is not cumulative. It's just convolutional neural networks.
What could be on the final as well?
Could be on the final, could be on the midterm. So therefore,
And will the final be cumulative?
the final will be cumulative.
Well, I feel like it's one of those I guess when it shows
Okay, so if we remove
well, I'm saying that you can just
what is the output?
All right, 2.5 more minutes. Oh, that one? Yep.
Do you actually create a new model each time you make a new?
Yes.
Like, how would you do the testing? Like, which models do you choose? Do you run all of them, or
You could do the best one. You could try and retrain a model with the same hyperparameters and everything, but with all of the training data.
and then for that, would you use the standard deviation and width of all of the training data for the testing?
Yes.
You do it out just
For that.
to that on the training data.
Yeah, basically, once you've got a model, you always use the whatever normalization that you're doing on the training data. You do exactly the same normalization for anything you're feeding it. So either when you deploy it to production, you'd still do that same. All right, guys, turn that in. Whatever you got, I appreciate it. And then I will give you things. You don't need to put the names on them, right? Your reward will be, if it's good enough, it will appear on an exam. Near you. Maybe next week, maybe the final. I'm passing out the homework, which is actually questions from a previous exam. And I'm also passing out assignment 8. Assignment 8, in a nutshell, is to implement dropout from scratch. So in Keras, you're going to write a dropout layer. I've given you the model for it. It doesn't do anything. In order to make sure that it's working, you are going to write unit tests for it. How many people have used unit tests before? Some. All right. Well, this would be good for you. So actually what I've provided you is a test case that has one unit test that is completely written, but which doesn't work, right? Because the code isn't in the dropout layer. And 4 tests which have names and just fail, but they describe what it is they're supposed to be testing. As far as I know, that should completely capture what your dropout layer needs to do. And then what you're going to do is actually put that dropout layer in a model. So you're going to compare, what if I use a built-in dropout layer versus my dropout layer? Is it in fact working right? That is it. Monday is a midterm review, and I will hand out the midterms.
Are you back on the old,
You can look at whatever you want, including the source code to the dropout layer, because it will not be very useful. Thank you. Thank you. And one fell down here.
Have you graded assignment 2?
Yes.
It's not graded mine. I checked and I did share it.
Can you send me an email?
Yeah.
It may be that I just missed, because if I don't look at the email, because I have to actually accept it from the email. So that may be. So yeah, definitely send me an email.
I just noticed you graded assignment 3, and I was like,
Yeah, no, it should be. How is it going now compared to a couple weeks ago?
Great.
Good.
It's really just a matter of being behind.
Okay.
Last assignment was quite a bit better, homework.
Yeah, homework. Quiz. Mm-hmm.